There is a molecule sitting on the surface of Pluto right now that does not appear anywhere in the entire catalog of known chemistry. Not in any lab on Earth, not on any other planet, moon, or asteroid ever studied. Scientists have narrowed down what it might be. They have not been able to prove it. And that is only the second strangest thing the James Webb Space Telescope found when it looked at Pluto for the very first time. Everybody, we need to talk about what just happened to our understanding of the smallest, coldest, most dismissed world in the solar system. For most of the last century, Pluto has been treated as an afterthought. A tiny frozen rock so far from the sun that sunlight there is roughly 1,000 times dimmer than it is here on Earth. That reputation just took a direct hit twice from the exact same set of observations. And the story of how we got here says almost as much about the limits of our instruments as it does about Pluto itself. Let's go back to where this all started, because the history matters more than most people realize. Pluto was discovered on February 18, 1930, by a 24-year-old American astronomer named Clyde Tombaugh, working at Lowell Observatory in Arizona, painstakingly comparing photographic plates of the night sky for any object that appeared to shift position against the fixed background of stars. For decades afterward, Pluto held the title of the 9th planet in the solar system, a distant, mysterious point of light that nobody could resolve into an actual surface, no matter how powerful the telescope pointed at it. That changed in 2006, when the International Astronomical Union formally redefined what counts as a planet, and Pluto, unable to meet the new criteria of having gravitationally cleared its orbital neighborhood, was reclassified as a dwarf planet. It's a decision that's still debated by scientists and the public alike today, but at the time, it effectively demoted Pluto from planet to afterthought in the public imagination, exactly at the moment when a spacecraft was already on its way to visit it for the first time. That spacecraft was New Horizons, launched by NASA in January 2006, just months before Pluto's reclassification. It spent 9.5 years crossing the solar system, and on July 14, 2015, it screamed past Pluto at more than 30,000 miles per hour, passing within about 2,500 kilometers of the surface in a single, irreversible flyby. There was no orbit, no second pass. One shot, gathered in a matter of hours, then transmitted back to Earth over the following 16 months because Pluto is so far away that even at the speed of light, a single message takes over 4 hours to arrive. What New Horizons found stunned nearly everyone involved in the mission. Instead of a dead, cratered ball of ice, Pluto turned out to be geologically alive, mountains of water ice rising several kilometers high. Vast glaciers made of nitrogen and methane, slowly flowing across the surface the way glaciers do on Earth. A massive, smooth, heart-shaped plain, later named Sputnik Planitia, so significant to Pluto's internal heat balance and rotational dynamics that scientists nicknamed it Pluto's beating heart, and wrapped around the entire planet a thin, hazy, blue-tinted atmosphere, visible in one of this mission's most iconic images, backlit by the sun as New Horizons looked back at Pluto from behind, revealing layer after layer of haze extending high above the surface. That image, more than almost any other from the entire mission, planted a question in the minds of planetary scientists that nobody had the tools to answer at the time. What was that haze actually doing? Was it just cosmetic? A thin layer of fog drifting passively above the ice? Or was it doing something functional, something that actually shaped the climate of the entire planet? Sputnik Planitia itself turned out to be central to that question, even before Webb ever got involved. That heart-shaped basin, roughly the size of Texas, is filled with a shifting sea of nitrogen ice that slowly convects, rising and sinking in cells, not unlike a lava lamp driven by the faint warmth trapped beneath the surface. As that nitrogen ice sublimates, turning directly from solid to gas under Pluto's extremely low atmospheric pressure, it feeds Pluto's thin atmosphere from below, while colder regions elsewhere on the surface pull nitrogen gas back down and refreeze it, in a slow, planet-wide cycle that researchers had already linked to seasonal winds and haze production years before Webb ever pointed its mirror at the system. It's part of why scientists nicknamed the basin Pluto's beating heart, since it doesn't just sit there. It actively regulates atmospheric pressure and composition across the whole planet, on a cycle tied to Pluto's 248-year orbit around the Sun. Understanding exactly how the haze interacts with that nitrogen cycle was one of the central questions Webb's 2022 and 2023 observations were specifically designed to help answer. New Horizons couldn't answer that question, and it's important to understand exactly why, because it's not a story about a mission failure. It's a story about a spacecraft doing exactly what it was built to do and running into the honest limits of 2006-era instrumentation. New Horizons was designed as a reconnaissance mission, built to survey Pluto's geology, map its surface, characterize its moons, and confirm the basic composition of its atmosphere during a single, fast pass. It was not equipped with an instrument sensitive enough to break Pluto's extraordinarily faint light down into the specific range of infrared wavelengths where haze particles reveal how they actually absorb and radiate heat. That gap in our knowledge sat unresolved for years, an entire category of Pluto's behavior that nobody possessed the sensitivity to properly measure. Enter the James Webb Space Telescope. Webb launched on Christmas Day 2021, and instead of orbiting Earth the way Hubble does, it sits nearly 1 million miles away, parked at a gravitationally stable point called the second Lagrange point, where the combined pull of the Earth and the Sun lets it stay in a fixed position relative to our planet, while a 5-layer sun shield roughly the size of a tennis court keeps its instruments shielded from any stray heat. Its primary mirror measures 5 meters across, built from 18 individual gold-coated hexagonal segments, more than 2.5 times the light-collecting area of Hubble's mirror. That size, combined with its isolation from Earth's own heat and light, is exactly what makes Webb sensitive enough to do something no previous telescope or spacecraft could manage: separate the impossibly faint thermal glow of a small, distant world like Pluto from the glare of everything else surrounding it. And specifically, the instrument responsible for this particular discovery is called MIRI, the Mid-Infrared Instrument, engineered to detect exactly the kind of faint thermal signals that had been sitting just out of reach for every previous mission. In 2022, an international team of researchers pointed Webb's MIRI instrument at the Pluto-Charon system for the first time, and immediately ran into a genuinely tricky technical problem. Pluto and its largest moon Charon are close enough together and far enough from Webb's mirror that their light tends to blur together in the telescope's data, their point spread functions overlapping, in a way that made it nearly impossible to cleanly separate what was coming from Pluto and what was coming from Charon. Researchers had to develop a careful extraction process, using precise positional data from NASA's own orbital calculations to isolate each world's contribution to the combined signal, and subtracting out the contamination each body's light was creating in the other's data. It's the kind of unglamorous, exacting technical work that never makes it into a headline, but without it, none of what came next would have been possible. Once that separation was achieved, the team captured rotational light curves of both worlds at wavelengths of 18, 21, and 25 micrometers throughout 2022, watching how the thermal brightness of each hemisphere changed as Pluto and Charon rotated. Then, in May 2023, Webb went further, capturing a full, high-resolution mid-infrared spectrum of Pluto spanning from 9 to 27 micrometers, a wavelength range that had simply never been explored for this world before in the history of astronomy. For the very first time, scientists had the actual data needed to test an idea that had been sitting on the shelf, unproven, for the better part of a decade. That idea belonged to Xi Zhang, a planetary scientist at the University of California, Santa Cruz. Back in 2017, working from the fresh data New Horizons had sent home 2 years earlier, Zhang's team proposed something bold. They suggested that Pluto's haze wasn't a passive cosmetic feature at all. They proposed it was actively running the planet's entire climate system, absorbing sunlight during Pluto's long day and radiating that heat back out into space as infrared energy, cooling the atmosphere far more efficiently and directly than the thin gases of the atmosphere itself ever could on their own. If true, that would make Pluto's atmosphere behave completely unlike every other atmosphere scientists had ever studied anywhere in the solar system, powered primarily by solid haze particles rather than the gas dynamics that control weather and temperature everywhere else, from Earth to Mars to Jupiter. It was an elegant hypothesis. It was also, at the time, completely untestable because the instrument capable of confirming or rejecting it simply didn't exist yet. When Webb's 2023 spectral data finally arrived, an international team led by Tanguy Bertrand at the Paris Observatory, working alongside Zhang and other collaborators, ran the numbers, and the results lined up with Zhang's decade-old prediction almost perfectly. Pluto's haze really was glowing in the mid-infrared exactly the way the models predicted it should, precisely the signature you would expect, if that haze was truly absorbing and radiating heat as the dominant force controlling the entire atmosphere. The findings, published in Nature Astronomy in 2025, stated plainly that the observed thermal fluxes indicated Pluto's haze is composed of Titan-like organic particles mixed with hydrocarbon and nitrile ices, and demonstrated conclusively that this haze largely controls Pluto's atmospheric heat balance. By comparing the light curve data against detailed thermal models, Bertrand's team was also able to place firm constraints on the thermal inertia, the emissivity, and the surface temperature of specific regions across both Pluto and Charon, numbers that had previously only been loosely estimated from older, lower-resolution observations made by the Spitzer and Herschel space telescopes years earlier. On Charon specifically, the new data revealed a genuinely striking split between its bright, water ice-covered plains and its dark, reddish polar regions, two surfaces behaving so differently in the thermal data that researchers say it points directly to a fundamentally different history and composition between the two zones. Zhang's own reaction to seeing his 8-year-old hypothesis confirmed this precisely and this quickly is on record, and it tells you how rare a moment like this actually is in planetary science. He said, "It isn't common to have a hypothesis confirmed so specifically," and that his team felt lucky and genuinely excited watching it happen. Bertrand, leading the newer analysis, described exactly what this makes Pluto in the broader context of the solar system. He called it a genuinely unique spot in how planetary atmospheres behave, offering scientists a rare chance to understand how haze functions in extreme environments, not just on Pluto, but potentially on Neptune's large moon Triton and Saturn's moon Titan as well, two other worlds with strikingly similar nitrogen and hydrocarbon-rich atmospheres. There's a detail buried in Zhang's explanation that deserves more attention than it usually gets, because it connects Pluto directly to our own planet's deep history. Before oxygen built up in Earth's atmosphere roughly 4 billion years ago, during what geologists call the Great Oxidation Event, our own planet's atmosphere was dominated by nitrogen and hydrocarbons, chemically similar in broad strokes to what Pluto's atmosphere looks like today. Studying exactly how haze particles behave in a nitrogen and hydrocarbon-dominated atmosphere on Pluto isn't just an exercise in cataloging a distant, frozen world. It's giving scientists a physical laboratory, 4 billion miles away, for understanding the kind of atmospheric chemistry Earth itself once had, long before there was anything alive on it to breathe. There's a broader reason this matters beyond Pluto alone. New Horizons didn't stop at Pluto in 2015. It kept flying deeper into the Kuiper Belt, and on New Year's Day 2019, it performed a second, even more distant flyby, this time of a small, reddish, snowman-shaped object called Arrokoth, roughly 1 billion miles beyond Pluto, the most distant object any spacecraft has ever explored up close. Arrokoth turned out to be a pristine, largely unaltered relic from the earliest days of the solar system's formation, and scientists studying it found its own version of a reddish surface coating remarkably similar in color to the material building up on Charon's poles. Understanding exactly how Pluto's haze behaves and exactly what compounds form when solar radiation and cosmic rays slowly cook simple ices over billions of years doesn't just tell us about one dwarf planet. It gives researchers a working chemical model for an entire population of small, frozen worlds scattered across the outer solar system, most of which we will likely never send a spacecraft to visit directly. But the haze confirmation wasn't even the strangest thing this same set of Webb observations turned up. Buried in that same 2022 and 2023 dataset, researchers found evidence of something New Horizons had only glimpsed in passing, and Webb was able to study in far greater detail, an active, ongoing transfer of material directly from Pluto's atmosphere onto the surface of Charon. Pluto's largest moon has no atmosphere of its own, and its dark, reddish polar caps have puzzled scientists since New Horizons first photographed them in 2015. Webb's newer data helped confirm the mechanism behind that coloring. Gas escaping from Pluto's thin atmosphere drifts across the gap between the two worlds and settles onto Charon's poles, where it's chemically transformed by sunlight and radiation over time into the reddish material visible in New Horizons' original images. Researchers studying the system describe it as an interaction that happens nowhere else in the entire solar system. One world's atmosphere actively painting the surface of its neighboring moon, a slow, continuous process, playing out in real time across the gap of Pluto and Charon's mutual orbit. Separate JWST observations, focused specifically on Charon, have even detected carbon dioxide and hydrogen peroxide embedded in its surface ice, adding further chemical detail to a moon that, before Webb, scientists could barely study independently of its much more famous neighbor at all. If real, published, peer-reviewed planetary science like this is what you come here for, subscribe now, because the strangest part of this story is still ahead. Because, layered directly on top of the haze discovery and the Pluto to Charon material transfer, in that same high-resolution 2023 spectral data, researchers found something they genuinely could not explain. At a razor-specific wavelength of about 11 micrometers, there's a dip in the light, an absorption line, meaning something on Pluto's surface is soaking up light at that exact wavelength, the same way every known chemical compound leaves behind its own unique spectral fingerprint. Researchers checked that fingerprint against every known ice, gas, and organic compound ever cataloged in the atmospheres of Pluto and Titan, ethane, ethylene, acetylene, propane, benzene, hydrogen cyanide, and found no match. The team stated directly in their published analysis that they could not identify any previously documented spectral band corresponding to the location of this particular absorption feature. In plain language, something on the surface of Pluto is made of a chemical compound that has never been formally identified anywhere else in the known universe. Here is where the mystery becomes genuinely strange rather than simply unexplained. That exact same 5, 11 micrometer absorption line turned up in Webb data of Saturn's moon Titan as well, a world that shares almost nothing else in common with Pluto. Titan orbits a gas giant, has a thick atmosphere with a surface pressure roughly 50 times greater than Earth's, and famously has actual liquid rivers and lakes of methane and ethane on its surface, the only other confirmed body in the solar system, besides Earth, known to host stable surface liquid. Pluto is a frozen dwarf planet roughly half Titan size, sitting alone in the isolation of the Kuiper Belt, 4 times farther from the Sun than Titan ever gets. 2 worlds with almost nothing in common, separated by billions of miles and completely different physical environments, both showing the exact same fingerprint of an unidentified molecule. Researchers ran careful checks to rule out the possibility that this signal was simply contamination from each world's atmosphere rather than something genuinely on the surface. If the absorption were coming from gas floating above the ground, it should appear stronger toward the edge of each world's visible disk, where starlight has to pass through more atmosphere before reaching the telescope. Instead, the team found the opposite pattern. The signal was consistently weaker at the edges of both Pluto and Titan and stronger toward the center of each disk, exactly the pattern you would expect if the absorption is coming from something sitting directly on the surface itself, embedded in the ice, rather than floating in the atmosphere above it. The 2 signals aren't perfectly identical either, and that difference might end up being the most important clue of all. On Pluto, the absorption line is roughly 3 times wider than the equivalent feature found on Titan, even though both dip to a broadly similar depth in the spectrum, somewhere between 4 and 5%. A wider absorption band like that usually points towards something about the physical environment the molecule is embedded in, rather than necessarily indicating a completely different chemical. Researchers considered whether Pluto's much colder surface temperature, somewhere between 30 and 60 degrees above absolute zero compared to Titan's 90 to 95 degrees, might explain that difference. It doesn't. Colder ice typically produces narrower absorption bands, not wider ones, meaning the temperature difference actually runs in the opposite direction from what was actually observed. The leading explanation researchers are now chasing involves something almost nobody thinks about when picturing Pluto quietly orbiting at the edge of the solar system: cosmic radiation. Pluto's atmosphere is dramatically thinner than Titan's, meaning it offers far less protective shielding for the surface underneath it. Streams of high-energy cosmic ray particles arriving from deep space can punch straight through that thin atmosphere and bombard Pluto's surface ice directly, penetrating anywhere from several centimeters to tens of centimeters deep, physically altering the crystal structure of whatever compound is producing this signal in ways that could plausibly widen its spectral fingerprint over time. Titan's dramatically thicker atmosphere would shield its own surface from that same level of bombardment almost entirely. If that theory holds up under further study, the underlying molecule itself might genuinely be the exact same compound on both worlds, simply weathered by 2 completely different radiation environments into 2 slightly different versions of the same fundamental chemical signature. As for what the compound itself actually is, researchers have narrowed the field down to a short list of genuine candidates without landing on a confirmed answer. Alans, a class of organic compounds known to absorb light in a closely matching part of the infrared spectrum, are among the leading suspects. Benzene, mixed together with other molecular species, remains on the table as well. So does keton, along with a family of compounds known to form specifically when methanol ice gets irradiated over extremely long periods of time. Exactly the kind of slow, patient chemical transformation you would expect billions of years of sunlight and cosmic ray bombardment to produce on a surface this ancient. To be clear about exactly where the science stands right now, this particular finding was uploaded to the preprint server arXiv in June 2026 and has not yet completed formal peer review. The researchers behind it have been explicit that considerably more work is needed before any of these candidate molecules can be confirmed as the actual source. So here's where all of this actually leaves us. James Webb pointed a mid-infrared instrument at a small, frozen world 4 billion miles from the Sun, doing something no telescope or spacecraft in the history of astronomy had ever done before. And in that single set of observations, it didn't just confirm one landmark hypothesis about how an entire planetary climate system works. It also documented an active, ongoing chemical relationship between Pluto and its largest moon that happens nowhere else in the solar system. And, layered directly on top of both of those findings, it stumbled onto a chemical signature that doesn't match anything in the entire known catalog of solar system chemistry, embedded in the surface of 2 worlds that otherwise share almost nothing in common. That isn't one discovery wearing a dramatic headline. That's 3 genuinely significant findings, stacked directly on top of each other, from a single patient set of observations. Of a planet most people stopped paying attention to the moment it lost its official planet status back in 2006. Pluto was never actually the boring, frozen afterthought it got reduced to in the public imagination. It just took nearly a century, one high-speed flyby spacecraft, and one telescope sitting 1,000,000 miles from Earth, finally equipped with the right instrument at the right sensitivity to prove exactly how wrong that reputation always was. Researchers are continuing to analyze this data right now, refining exactly how Pluto's haze-driven climate compares to the atmospheres of Titan and Triton, tracking the slow chemical transformation happening on Charon's poles in real time, and racing to identify the exact molecule sitting on two completely different worlds that nobody on Earth has ever been able to name. There's more coming too. Webb's observing schedule is planned years in advance through a competitive proposal process, and researchers on the Pluto team have already indicated they intend to pursue follow-up observations, specifically targeting that unexplained 11 micrometer signal, hoping additional spectral coverage and longer integration times might finally pin down which of the candidate molecules, allenes, benzene mixtures, ketene, or irradiated methanol byproducts actually matches the data cleanly enough to call it confirmed. Laboratory work is happening in parallel, with planetary scientists on Earth attempting to recreate Pluto-like surface conditions, irradiating candidate ices with cosmic ray equivalent particle beams in vacuum chambers cooled to nearly absolute zero, trying to reproduce that exact widened absorption signature under controlled conditions here on the ground rather than 4 billion miles away. If that laboratory approach succeeds, it wouldn't just identify a new molecule, it would hand scientists a genuinely new tool for reading the radiation history written into the surface ice of small, distant worlds all across the solar system, Pluto included. If stories like this, real published science, genuine unresolved mysteries, and zero exaggeration are what you come here for, subscribe and turn on notifications. Because between the confirmed haze discovery, the ongoing Pluto-Charon material exchange, and whatever this unidentified compound eventually turns out to be, this small distant world at the edge of the solar system is nowhere near finished surprising us.